Good morning, all. I am very happy, and it's a pleasure for me and NGSoft hosting our partner ESRD and its CEO, Mr. Riccardo Actis, for this series of webinars dedicated to SESA, Smart Engineering Simulation App. We do believe in this very interesting technology, and we think it will be part of the future of concepts like simulation governance and simulation democratization. 2 weeks ago, we opened this series with Webinar 1, an introduction about what are Smart Engineering Simulation App. Today, Riccardo will explore functional and technical requirements for SimApps. Next appointments are at the end of July, during which we will touch topics like select, create, and deploy simulation apps. And early in September, then, we will close the series with examples and reference case studies. Now it is a pleasure for me to introduce Mr. Riccardo Actis, CEO of ESRD, St. Louis. Thank you.
Good afternoon, everybody. Thank you, Luca, for the introduction. Today we start with a Webinar 2 of the series in which we'll address the technical requirement for simulation apps. A brief overview of what we cover in Webinar 1, for those of you that could not attend. We address the reasons why simulations has historically been performed by specialists and review why legacy final elements products struggle with standardizing and automating simulation processes due to the inherent complexity and their inability to measure solution quality in a posteriori mode. We also define what are smart simulation apps, why they are important, what are the benefits, what are the challenges in creating them and in deploying them. And if you're interested in a replay of that webinar, one is available in the link indicated there that will be made available to you after the presentation. I would like to start with a few words about ESRD. Engineering Software Research and Development was founded in 1889 and has headquarters in St. Louis, Missouri, in the United States. We focus exclusively on computer-aided engineering. Our goal is reliability through numerical simulation governance, and that means verification through and control of the errors of approximation, validation through the estimation and control of the errors associated with the selection of mathematical models, and standardization through knowledge capture and simplicity. We produce engineering software for numerical simulation in the area of computational solid mechanics, primarily on aerospace and defense application, but over the last years, smart engineering simulation apps have been developed for different industries. More information is available on our website if you would like to learn more about ESRD. This is an example of one simulation app in a product that we have been deploying for several years called the CAE-Handbook. And what is indicated here is a typical composite joint, which is known as the pi joint. And the objective of this particular application is to study the effect of the lamination in the strength of the joint. Some of the characteristics of the joint that make it particularly difficult to analyze is the fact that every ply has to be specifically included into the model in order to determine of the influence of the lamination. And as you can see on those details, elements become with very large aspect ratios. So unless the underlying technology supports, this is a very difficult task to perform. And this can be deployed for use for engineers which are not specialists. What is the focus of Webinar 2? Basically, there are two aspects that we'd like to review. One is the simulation function for knowledge capture, modeling, and prediction. and the other are the specific technical requirements from simulation apps in terms of simplicity, accuracy, efficiency, and reliability. And the terms are defined there so that they give you an idea of what we are going to be discussing. The simulation functions can be summarized in this diagram, in which we have a physical object that for which we want to obtain some information, and the conceptualization process, which is part of the knowledge capture, results in a mathematical model, which is then solved by defining a method to obtain a numerical solution. And that's what we call the numerical approximation to the exact solution of the problem. The numerical solution of a finite element analysis is a displacement field, so extraction procedures are required to obtain the quantities of interest from which predictions are made. This is the foundation, this is the basic of the simulation function, and the technical requirements within the simulation function for simulation apps is they have to be simple, standard, accurate and complete, fast and efficient, robust and reliable, and we will see in a moment. Before I can get into those details, I'd like to introduce the definition of simulation governance, which is the exercise of command and control over all aspects of numerical simulation. In short, what we mean is that the procedures of simulation governance include the proper formulation of mathematical models, the adoption of the best available simulation technologies, and, very importantly, data and solution verification. The goal is to enhance and ensure the reliability of prediction based on numerical simulation. It's always expected that when a result of numerical simulation is produced, the reliability should be hand-on-hand, and that has to be guaranteed by the procedure. In other words, to ensure the level of reliability needed for professional use, simulation app must incorporate a posteriori estimation of relative error. This is also known as solution verification, which is an essential technical requirement of simulation governance, and we will elaborate a little bit on that shortly. Do we really need solution verification, since users can always consult with an expert if the results are wrong? This is a fair question to ask. Is this argument valid? And the answer is no, for the following. If the assessment of the quality of a solution depends on the subjective opinion of the expert analyst, the same expert opinion is needed to determine when the solution may be wrong. The user may not be qualified to make that determination. For that reason, we have to have very strict technical requirements for the development and deployment of smart simulation apps, as we will see now. What you see here, the Albert Einstein quote, if you can explain it simply, you don't understand it well enough. I hope that we can make the explanation simple enough that it's understandable. If not, you can ask as many questions as you want at the end. Simulation apps, we review the simulation functions, knowledge capture, conceptualization, modeling, numerical approximation, and prediction. Requires that the technology foundation used for simulation apps should be simple and standard, accurate and complete, fast and efficient, robust and reliable. And simulation apps are smart if they satisfy the technical requirements of simulation governance. And we introduced already the concept. Let's now review this technical requirements. By simple, we mean that the supporting technology should provide with a minimal element library to capture topology, which should be feasible to use three-dimensional solid elements throughout, and it should provide a hierarchy modeling framework that facilitates the deployment of these applications. A standard in that we should apply the principles of numerical simulation only, in which the idealization is separate from the approximation, and it must support high fidelity multi-scale analysis on the same mesh. That means that all the elements, the same element can be used for all analysis types. Just to give you a brief idea of what we mean the principles of numerical simulation, the development of the knowledge base of the finite element method and the corresponding technical requirement for verification and validation are indicated here in this timeline, which starts with the first paper on the finite element published in 1956. Another important event that occurred early on in the process in 1965 was the NASA request for proposal for a structural analysis software. That was the from that proposal, what the NASA structural analysis program was born, also known as NASTRAN. The first mathematical papers on the finite element method appeared in the early 1970s. At that time is when we call that we refer to this as the parallel develops in the 1970s. Legacy finite element analysis was introduced in the early 70s. The concept of finite element modeling was introduced. Tuning was considered to be a proper approach to overcome the difficulties associated with the utilization of the finite element method, and predictions were produced without a posteriori solution verification. Basically, this established a process by which only experts can operate in this modality. A later development, if you look at the timeline on the left, the proof of convergence, critical proof of convergence was produced in 1981, and demonstration on exponential rate of convergence appeared in 1984. So that's why the track of numerical simulation, the proper procedure of numerical simulation, can be traced to around the late 1980s. That numerical simulation, also from the work done in the 1990s with implementation of model hierarchicities, is what is indicated here with hierarchy space and hierarchy model, which is the foundation for this numerical simulation approach. And the outcome of that is that the prediction occurred with solution verification. And this solution verification became really important together with the validation in the early 2000s, and the ASME produced a guide for verification and validation procedures in 2006, and NASA produced some standard for model and simulation in 2008. So that when we refer to numerical simulation, we refer to the green track, not to the red track. Accuracy, we mean, and completeness means accurate numerical has to be accompanied always with solution verification. Otherwise, the deployment of such application is very dangerous. And that means objective measure of solution quantity, the solution quality every time, not as a priori activity, but as a posterior activity. Every time a solution is produced, it has to be an objective measure of the quality of the approximation. Feedback when the answer exceeds rules or is wrong, and high resolution results should be possible for low density meshes, so the user, which may not be an expert in finite elements, can rely on the results obtained from the application. Complete in the sense that one model should be enough for a structural response and detailed stress analysis, with continuous solutions available for post-processing, and with the convergence assessments of any function, anywhere, and anytime. In order to illustrate that idea, consider this very simple problem, in which it's a contact problem, in which a large clevis is contained within a housing of an aircraft, and in this particular case, the goal was to assess the effect of rework on the lip of the housing to determine the influence on the maximum stress that was the characterizing parameter for the fatigue life of the component. Corrosion was detected in this component, and before the repair was initiated, it was decided to do an analysis to verify that after removing the corroded material, the component can take the load and have the proper fatigue life. What you see on the right is a typical finite element analysis result. Is a contour plot with the stress, and what I'm showing here is the mesh that was used in this case. On the left corner, you see a three-dimensional cut, and only the symmetric part is shown. The idea here is this mesh good enough to produce this result? And the answer to that is simply that yes, if you have the ability to demonstrate that the quantity of interest, in this case the first principal state which drives the fatigue life, has converged. That means as the number of degrees of freedom was increased on a fixed mesh, the results of the analysis show that the first principal state is convergent to a limit value. And that's what we mean by high resolution result for low density meshes. Regarding the fast and efficient, fast means that simplified modeling and live processes means fewer reruns tweaking the mesh, speed up the process of creation, and speed up the solution. Fast automatic sequence of solution for error control without user intervention. That means that once the model is ready to be solved, the computer takes over and the sequence of solution is produced automatically. This is a fast process, and the convergent feedback for any result in a way in the model can be easily obtained. Efficient means that large 3D solid models for detailed stress analysis are feasible. No need to mix shell and solid. This is a very common practice in large structural components, but also one that requires a lot of expertise to understand and get it correctly. And same elements as we mentioned for analysis type also contributes to the efficiency of the process. What you see here is a typical section of a portion of a wing, and if we look inside at some of the details, one of the problems with this type of structure is the scale issue. You see structural elements that are relatively large and small elements such as fasteners, holes, and when you also want to include the clearance, which is a fraction of the size of the hole, then you can see immediately the scale problem. So how a model like this can be properly analyzed. On the back side, you see the rib. In this case, it's upper skin and the lower skin are bonded to the flange. This rib is connected to the main spar by means of fasteners that connect the top and bottom skins to the flange of the spar, and by a shear clip that connects the web of the spar to the structure in the back by means of fasteners. There are 5 fasteners on the shear clip, and there are 3 in this case for this detail, 3 fasteners connecting to the main spar. And the similar situation occurs in the front. One of the complexities of this problem, or the reason we had to develop this particular application, was that engineers wanted to know what is the efficiency of the shear clip in transfer the shearing, because the dimensions of these components were such that the traditional calculations were not capable of determining how effective was the shear clip in transferring the shear. And what we were able to demonstrate that by just changing the level of interference or clearance of the fastener, the shear clip could take from almost the full load to no load at all, which was a big help for the engineers having to make this design decision on this component. And as you can see, now these are the meshes that are used. These are very efficient meshes for 3-dimensional solids, a single element through the thickness of the plate of the component, the thin components, and this is a very challenging problem. For and fault tolerant and reliable, that means that can be used both by a specialist and non-expert alike with confidence, because users receive an objective measure of solution quantity without an expert on call. As an example, this is a application that ESRD has developed called the CAE-Handbook, and what we see here is a browser that allows the user to select from a library of C-maps the one of interest. Whenever one of the apps is selected, there is a document that explains to the user what is the goal of the analysis, what are expected results, and what are the options for controlling this solution. Once one is selected, is loaded into the application that has a very simple and intuitive graphical user interface that allows the manipulation of the parameters that are shown here on the right. There's always an icon that relates to what the parameters mean. has additional information that is available. The user simply manipulates the parameters in this case, and as you see, update the model to represent the current configuration that is of interest for analyzing. And once this is done, the only thing you have to do is to click the Solve button, and when that is done, the solution appears. And what is very important is that the objective measure of quality or not by a non-expert. So what is the enabled technology behind the development of these apps and the satisfaction of these technical requirements? Is an FEA technology which is based on hierarchy modeling framework and hierarchy finite spaces with extremely simple library where there is no need to search for the right elements because the elements are only there to provide the topological description of the solution domain. High resolution, high fidelity, high resolution are possible solution mesh, for example, and continuous results are made available through our entire model. Using these hierarchy finite element spaces, the quality of the solution is fairly constant throughout the whole domain, what it means that the extractions of the results of interest are not limited to some special points in elements as traditional finite elements do. Post-processing live means that it's a live connection between the GUI and the solution, and the solution is stored in a way that any post-processing that the user needs can be generated on the fly anywhere at any time after the solution was obtained, and there are automatic reports of objective measure of accuracy. Just to give you an idea that we have been tackling with this technology that are outside of the reach of traditional finite element implementation. This is an example of a wing of an aircraft. This is a closing rib of a large aircraft, and which is shown here on the right. And the objective was to analyze a detail where this fitting interacts or is inserted into the rib. Just to have an idea of the detail, let me show you the backside of this structure. When you see that the fitting is connected with several fasteners, there's some details here. For example, this represents a seal groove. That means that all they have to, and since this fitting is going through the rib, also it has to be perfectly sealed to prevent fuel leak. The problem was that on this back part, a crack developed, and they wanted to understand what was the threat distribution before the crack developed and what happened after the crack was introduced. It shows an idea of the global local analysis concept, meaning that the structure, the local parent black arrows represent the loads that were brought into the local system by the solution of a global model that represented the complete wing of the aircraft. Just to show the area of the primary interest, removing the fitting, so all the holes, each one of these holes is full with the fastener inside, so contact solution is required, and the seal groove is on one side of the structure of the rib, and you see this is a machine from a single part of material, a single piece of material. The results are shown here, and again, in this case on the left, the figure shows the thread distribution. This thread distribution is shown as comes from the software. There is no smoothing or any other massaging of the data, and that is another measure of the quality. The errors in this case represent the direction of the principal stress that were required to know where to insert the crack for the follow-up analysis. Just this problem, just to give you an idea, is a multi-body contact problem of about 5 million degrees of freedom. So what are the benefits of MR simulation apps? We here look at this from the point of view of who is the user. For the special analyst, making this class of problem of simulation problem easier to analyze, more accurate and faster to solve. to support increasing complexity of products and demanding design cycles. Also for the specialist, creating new high-value role for the specialist to define, author simulation apps across their organization and industry, and in that way creating intellectual property for themselves and for the employer. If we move now to a different group, for example, designers and engineers, the benefits are that it makes routine classes of design analysis problems solvable as the same way as they did for years when using handbooks and design curves produced by method groups or industry standard organizations. For new engineers, empower them to be productive sooner with access to reliable technology, capturing the institutional knowledge and best practices with simulation apps. In summary, engineering simulation apps provide a framework for the accumulation and preservation of organizational knowledge and standardization and automation of simulation workflows. For specialists and non-specialists alike, they fit into existing analysis process, capture best practices, produce consistent results by approved procedures, remove many sources of errors and judgment, and increase productivity. Engineering simulation apps, in order to be smart, they need to enable simple, accurate, efficient, robust, and reliable simulations with built-in quality assurance. And this is a very important aspect. Simulation apps must incorporate solution verification procedures for all reported results, which is an essential technical requirement. Without this, the deployment of simulation apps into the hands of non-expert can be risky, if not negligent. When deployed in this way, smart simulation applications provide many benefits for authors, users, and organizations. And if you would like to have more information about these technical requirements, there is a paper available in our website for download, and with information is given here. I would like to thank you for your attention, and open the floor for any question that you might have. And just for those of you like myself, remember the old good times of simple engineering. This is a little example in a job format of a simulation app that we used to use many years ago. And with that, I return the control to Luca. Thank you.
Ricardo, I want to thank you very much for this presentation, and it was very clearly defined solutions for some of the issues that every analyst faces on a daily basis. And let me just remind the next appointment that will be on July the 28th with our third webinar of the series, where Ricardo will tell us about something to select, create, test, and deploy simulation apps using ESRD technologies. Thanks again, and goodbye.